Hey Brandon, can I get a sound check?
Yeah, I can hear you.
Okay, awesome, thanks. Hey, did you ever try your GoPro as a webcam?
No, I haven't tried it.
Yeah, it might be a little bit more complicated, the older models. So Brandon, what year are you in?
I'm unfortunately in my 4th year. It's just been crazy trying to get classes. I messed up by doing all my GEs first.
I was gonna say, so you've had the experience, sort of like the like actually being to classes.
Correct. Yeah, that's something that is baffling to me, to think that some of the people in this class haven't even physically been to a Cal Poly classroom.
Yeah, that's interesting. Yeah, it's tough getting, man, it is tough. I would not make it as a student again.
Yeah, I for one of the labs, it expected us to use like an oscilloscope. I'm like, I don't know how they would expect someone to fully understand using an oscilloscope from a YouTube video lab.
Yeah, that's a little weird. I don't know. So how many, I know this is probably a bad question to ask you, how many more years you got?
I kind of projected with my last time looking at my classes like 2023, but I don't even know. It's because I only get general registration, so I keep falling into the issue as well, where priority registration fills up all the classes before even I have an open enrollment appointment. So
Well, what's the story with that? Is that, I don't know any of these things at Cal Poly. So you're saying priority goes to who?
I'm not 100% sure, but I know, just speaking to some of my friends, how if you have certain scholarships or grants, you get priority registration, or students who also do the 4-year pledge, they would get priority registration. So they get an earlier enrollment window, typically only like 24 hours or so. But that's usually like 2 or 3 weeks before general registration.
Mm.
And then also based on your year, I believe you get like 1 or 2 week fluctuations, or like kind of a window prior to general registration as well.
That's intense. Man, my dog is going nuts. Yeah, well. Just gotta, I guess, just gotta keep putting one foot in front of the other.
Yeah, part of the reason it's taken me a while as well is I work at UPS. So I started off as just like part-time. So I was able to put a lot of time into school, and then I became a part-time supervisor. So I did a little bit more hours, and now I'm doing full-time. So yeah, I've got like 40 plus hours a week and trying to balance school.
Wow. I have no idea how you do it, man.
Yeah, at least the fortunate situation that I have to look forward to is it is already expected and laid out. Once I actually hold the degree, then I already have a locked in, well, not, I shouldn't say locked in, but all my supervisors, managers above me already have full recommendation for me to be a full-time supervisor as well.
Cool. So jobs waiting for, so is that, but are you gonna use your degree there?
Yeah, I'm actually in the building and systems engineering department right now.
Oh, great. Oh, that's awesome. Well, I think then that's like, man, I think you're doing the right thing.
Yeah, I actually work, it, it's the newest facility, in Southern California. It's called Empire. It's a huge 1 million square foot automated hub. So we use like Rockwell automation, PLCs, like Allen Bradley variable frequency drives. And fortunately, I have the title of automation specialist, which, though in an industrial field, having the name like specialist would make it seem like I'm actually the one installing them. That's not actually the case. I'm just more of like the field troubleshooter, for any sort of like sort deficiency, and then anything that we can't resolve like locally within several hours, that's when we get a vendor out. But
So, wow, awesome. Love to see what that looks like. Huh. Interesting. Do you guys, yeah, anyway, that's probably something that, is there like a YouTube or something from like the vendor that shows off how their stuff works?
kind of ironically, they don't like that stuff being publicized at all, for proprietary reasons. But what I find ironic about it is a lot of the tech that we use is still like relatively leading edge, but still maybe half a decade old at this point. So it's not tip of the spear. Whereas like I feel Amazon invests a lot more money into that. UPS is more people based. So they don't spend as much of the money on that, but it still has pretty remarkable technology in it. Like, for example, we use on the preload sorts. That's the sort that we actually load the package cars and get the drivers, car set up to do their routes. Each package gets its own preload assist label, and those are applied while the belt is moving. So it's not somebody actually sticking those. It's an automated piece of equipment shooting labels called a high-speed label applicator.
Huh.
So that's just like one example of, we have belts moving at 540 feet per minute, getting a label air blasted onto it as it's traveling down the belt.
Air blast. Wow, so it's not like rolled on it or something. Wow. Air blast.
No, and that's just because each package has completely different dimensions. So if you had like a roller, or and even completely different weight, so you might have an adhesive like roller that would actually grab a package and then get caught up into the roll. So the reason it's being air blasted is because, like I said, different package types, you're guaranteeing that at least it's not going to get caught up in the equipment or disrupt the surfaces going on. Worst case scenario, you're just shooting the label onto the belt, which is typically what we end up seeing.
How does it know what is it? Is there some indication on the package what the label should be?
Yeah, so it's really simple, just photo eyes and encoders for knowing where the package is located on the belt. So it flags a photo eye. We already know the belt speed based off of the encoder, which is communicating to the PLC. So all that programming is already determined into it. So we know belt's moving at 450 feet per minute. This photo eye was flagged for this many seconds or pulses. So therefore we know this is a 17-inch long package. It'll then flag another photo eye, which illuminates a 6-sided camera tunnel, which the cameras are image code readers. So those have, again, another like algorithm built into them to identify some of the 1-dimensional and 2-dimensional barcodes. So at that point, it's then communicating to another server and then associating that to a destination. So it'll say, all right, this is going to Laguna, California. Based off of that, it communicates back to the PLC and it says, all right, Laguna, California has an allocated destination for this system, say shoot 1400. So now it already knows this is Laguna, California, and it's destined to go down to shoot 1400. And based off of that information, it already knows, like I said, communicating back to the server, all of the shipper information, you know, who it's going to, their address, and all of that. It's it's remarkable to think that within like 15 feet of belt length, it's able to retrieve all that information and apply a label.
And so you have, there's like 1,400 chutes that goes, you just have all these things that it goes down in different places? Or is it just-
1400 in this scenario that I was using, we have Metro runout belts, and I'm speaking specifically in the case of like for our preload, which is delivering to the package cars. Our hub will also process large 53-foot semi-trailers. So, but in the scenario that I provided, 1400 would just basically say this is our Metro line labeled M4, being the 4th Metro conveyor belt. And you have, I'm not sure why they start in the 1000s, but it's basically going from 1400 to, I believe it's like 30 package cars on either side. So there's like 60 package cars that it can divert to.
Wow. Man, amazing. What are your thoughts on the whole business of delivering the drones and all that stuff? Is that something that, I mean, I obviously probably, you can't speak for UPS, but what are your, like, do you think is that something that's realistic? Is it, I don't even know if it's something you work, that you have any visibility to or thoughts about?
The only thing I know of is this, what obviously what the news releases about it, but like my opinion of it, I don't think that it's very realistic. I think it's kind of like a niche item, just like ordering small stuff like vitamins or just like very lightweight, just low value goods. So it's kind of a high expense, high risk investment for Amazon for something with, like I said, most likely very cheap, low budget items, unless they're hoping to sell like a lot of headphones or earbuds, like small tech. That would be in my opinion, the only way that they would be able to justify such high risk for worrying about somebody swatting down a drone or something like that.
I see. Interesting. Yeah. I thought during the pandemic days, the sort of the height of the pandemic, I thought it would be like it kind of started making a little bit more sense just because, that it was hard to get people, just maybe not safe for people to be at work and so on. So it'd say, okay, you want to take people out of the loop and somehow deliver in some other way. But yeah, it seems like the payloads, if for drones, typically, I don't know if the payload's a problem, but at least the drones I've seen, they don't have a huge payload to deliver. But yeah, and like you said, there's like risks of stuff just going down, huh?
Yeah, I feel like if anything, it would still, like for the future, be more ground travel. I just feel like there's a lot of risks and hazards and obstacles with something like an aerial drone to deliver packages.
Yeah.
And I could be completely wrong. I mean, drones were one of my hobbies for a little bit, but I just know that the FAA has a lot of pushback for that kind of stuff.
Yeah. Yeah. Yeah, I agree. I was really excited about drones for a while, and then I don't know, it just seemed like they're maybe because of legislation or for other reasons, there's like a lot of stuff. There seem to be a lot of limitations that got created one way or another. So yeah, interesting. Well, thank God explosive deliveries are what do you call it, prohibited by law. Otherwise you'd have drones essentially dropping bombs on people too. Cool. Okay, Brandon, thanks a lot. That was good education about UPS.
Yeah.
It is
Yeah, no problem.
it is mind-boggling, but also I guess shows you how like when the financial incentives are there, that stuff just happens, which is pretty cool.
Yeah, I mean, without being too much of a business insider, uh, joking, of course, but I mean, automation is only going to continue to expand with UPS. So I would just like the stock is just going to continue to rise because UPS is going to continue to expand in that regard.
Yeah, yeah, makes sense. Makes sense. Cool. All right, guys. Thanks, Brandon. So, guys, we're gonna like get started here to keep going. Hopefully, I'm hoping to kind of like manage to. We're kind of like almost done with bipolar transistors. So I'm hoping we're gonna get done with the basics of bipolar transistors today, and then we're gonna move to more details of bipolar schematic design in chapter 5 from next week. So you guys are not particularly talkative, neither is any of my other classes. I guess this is the bane of being on the internet. So I don't know for sure, but again, when I was taking this class, just about now, I was like very, very confused about what the heck small signal models are, why we're looking at them, that kind of thing. So I keep trying to like come at it at different angles repeatedly to hope that it kind of like somehow it's just something that's hard to convey, and until you guys are actually designing circuits for a living, or maybe going into more advanced classes, whatever, it's just sort of hard to kind of see what we're doing here. But these are sort of like, because we're building up stages for you guys to be able to do that. So anyway, I just keep kind of coming back to it over and over again and trying different angles to get you guys to understand what we're doing. So sorry if I'm like a broken record. So again and again in this class, the idea here is that, as opposed to some other classes you guys might be taking, where you start with a model of a device, or say, or electromagnetics, or some understanding of something, and you develop a more and more realistic model of how that device works. We're not going in that direction in this class. We're actually going the opposite way. What we're doing is we're starting from, call it realistic, call it not, whatever, some kind of a semi-physical model. So we're starting with, for example, this model of this device that's made from semiconductors. It has, doping concentrations, and it's, an N-type material, P-type material, N-type material, and that there is some electric fields. We talk about electric fields here, and doping concentrations. I don't know, like donors and acceptors, and charge of an electron, and the width of the device, whatever we're talking about here, about the physical implementation of this device. Sort of, this is at the sort of this device physics, semiconductor physics implementation. And we're actually going to we're actually creating a simplified model of this thing, because we want to be able to look at how multiple iterations of this device are used to make a more complex system. And the only way to do that is to build simpler physical models or simpler models. It's not even a physical model. Simpler models of how this thing works, so you can build more and more complicated circuitry with this. If we were going to use models that were all encompassing, they had, n levels of complexity, that you know, that they explained everything in your device, like you just would not be able to build a circuit with, you know, 20 devices, or as you build, you know, logic circuits, you know, logic chip in your cell phone is 20 billion of transistors. Like you couldn't build, like it just could not deal with that. So anyway, so that's where we're starting. And then where we're going in this chapter was to say sort of the next level of simplification, as we said, okay, well, this is, we're gonna give this the schematic. I don't know what kind of space you think a schematic is. Schematic is maybe logical space, it might be mathematical space, it's a systems space. It's a way to sort of give a different perspective. It's a bunch of actual semiconductor devices that are very complex, but we're giving them a simple model, you know, symbol and relatively simple model. Okay, so we basically, this is the schematic view of this more complicated model of what this thing is. And then we're continuing to make this even, so this has, you know, represents, you know, two junctions that are sort of back to back with a very narrow middle area. And so the two junctions are talking to each other, and it's a 3-terminal device. So means that you could, you know, you have 3 voltages that you could, you know, connect to 3 terminals you can connect to, and each one of those you could put a voltage, or, you know, check for a current, or put a current in, put a voltage. So there's a lot of permutations that you could put on this device. You could, you know, make the collector higher than the base, then the emitter is higher than either one, or whatever. So at least if you just look at the voltages, you would have like at least 8 different permutations of which of these, you know, which one of these would be high, low, etc. Actually, probably, I take that back. It's many more, right? Because you're actually talking about voltages, and they could be anything. So we're further simplifying this, okay, and say that a useful, or a particularly useful method of using this device is when you bias it in the forward active mode. And so we're further like narrowing down this model, making it simpler. And that's basically saying base emitter junction is forward biased plus base collector junction is reverse biased. So every bipolar circuit you'll see in this class, probably for the next several classes, possibly for the rest of your life, the bipolar transistor will be operating in this mode. I'm sorry, guys, my dog is going off again. Let me go close one more set of drapes. I'll be right back. Hold that thought. Sorry about that, guys. She always finds a hole to look out. the neighbors. Anyhow, so basically we're further simplifying this thing by saying, look, and I, maybe I'm wrong, maybe somewhere down the line this class will see something other than forward active, but for by and large, we're simplifying it even more by saying we're going to operate it in this mode and this mode only. Okay, and once you do that, okay, so what does this mean? That this forward active mode, this forward active mode means that if I look at the VBE, so this is the base, so this is VBE, it's from here to here. If I look at that versus the collector current is flowing in here. Curve, sitting somewhere kind of out here. Okay, if I'm in this forward active mode. And that I can use this model now for the bipolar transistor. Now, this is already getting to be a fairly simplified model, very simplified model, which is that you have a current source at the output that represents the collector current. So this is the current coming out of here. Oops, the current basically going in, sorry. So it's because it's current going into the device. So it's going like this in to this end, and use our, this equation, which we use we've been looking at quite a bit. So that is that. And then we have a sort of a model to create a base current. This diode, all it's doing is trying to model the base current that you would get if you had a collector current. And that would be just, so this I sub B is just I sub B is I sub C over beta. And beta is a constant. It represents the current gain. Constant represents current gain from base to collector. And again, for this class, for the rest of your life, it's something, it's just a number. Like, and in this class, typically it ends up being 100. Because, these devices have been built to get a lot of current gain from base to collector. Okay, so this ends up being collector. This is the emitter node. And this is the base node. So, okay, so I'll come back to this in a bit. So again, so we're going from this relatively complex model to a less complex model. And then we're saying by biasing this thing in a particular way, by putting the right voltages on the base, emitter, and collector, we're going to even create a simpler model, which is this model, okay? Well, it still looks pretty complex, but, imagine if we were trying to build circuits off of doping concentrations and electric fields, et cetera. So, yeah, exponential factors are still difficult to deal with once you put, 2 of these, 3 of these, 4 of these devices together. But again, better than the alternatives here. We're just trying to simplify our life simpler and simpler, okay? So now, okay, so that was a leading statement because now we're saying, boy, even this is like too complicated because it has this exponential characteristics and so on and so forth. So we are going to even build or create a simpler representation. And we're going to call that's going to be the small signal model. And what that does is it just says that I'm going to make, I'm going to redraw this curve of VBE. Well, let me make it bigger. Same curve I drew here. I'm just gonna. That's big. So same curve. And we're still operating in this mode. So notice, by the way, that none of these is like, I'm just kind of making it drilling, like making a more and more limited model in some way. So it's simpler. Why is it simpler? Because I'm limiting the functionality, right? So it's simpler because I've only limited the voltages that I can put on this device. That's why this is simpler. And this is going to be simpler even, because what I'm saying is I'm going to put this device, make sort of bias it. So this would be so-called bias point. So this bias point, I'm going to give a certain constant VBE, I'm going to call it, let's call it V bias, because that's a. So this would be something that doesn't change. And I'm only going to operate this device around a very small region around this bias point. So my input to this device is not going to be, several hundred millivolts. It's not going to be a volt. It's going to be several tens of millivolts. So it's just going to be wiggling around here. That means that I can just pretend that that basically, that voltage. So if I look in this horizontal axis, my delta V here is only going to be wiggling around the small point around the bias point. That means that my current is only going to wiggle around. So as I'm moving around here, my current is only going to move around here, around this curve. And that this is going to be, if I zoom in enough here, instead of this looking like an exponential, it looks like a line. But just around this point, it looks like a line. If I'm biased around here, if I'm biased here, it's going to look like, still going to look like a line. It'll just be a different slope line than here. Okay, but so I could bias it here and just wiggle around here, but it gives me a different slope. And if I do that, I can pretend like I can take this model that has exponentials and things like that, as we all know, is kind of difficult to deal with. And I'm going to just be able to turn that into multiplication. And put in a resistor, it'll be a current source, but the current source just looks like a multiplication from input to output. And that's gonna look like this. So it's gonna have a resistor. So instead of a diode, because I'm going, I'm gonna do the same thing with the small signal model of the diode, wiggle it around a very small area and pretend like, it's a resistor with a certain resistance. So it's going to have resistance R sub pi. So this will be the base. And then my collector is going to have a GM. It's just going to have a constant times the input. So this V pi, V pi is the input. I don't know why they call it V pi, just the name, it's kind of stuck. So this is the emitter. This is the collector. And this G sub n is I sub c over V sub t. This V sub t, you guys know, is a constant, or at a particular temperature. This is 26 millivolts at room temperature. And then I sub c, your bias point is setting your I sub c. Okay, it could be here, could be this I sub c, could be this I sub c. So it just depends. And notice that as you increase I sub c, so as you go up this curve, after you bias this device up this curve, you get a higher transconductance. And that means you get for the same change in input voltage, you get a higher change in current, which makes sense. You're going up an exponential curve, okay? And then if you get a small up here, is you get a sharper slope. So if you got a small change in the horizontal direction, you get a big change in the vertical direction. Here you get smaller change in the horizontal direction, doesn't give you as much of a change in the vertical direction. What else do I want to say? Okay, and then you basically bias it by making sure you have some kind of a constant thing here where you're writing a voltage on top of it. What else do I want to say? Okay, I'm going to say also R sub pi equation is this beta over G sub m. And so that's my beta. It's just a constant. So I have a much simpler model here. Now compare these two. Whoops. So this guy, I have a resistor and a current source, but the current source is just multiplying a constant by the input. And here I have a diode and I have a sort of exponential relationship. So again, I'm narrowing the operating modes and coming up with a simpler model. And like a lot of the homework is kind of trying to rub your nose into the fact that, exponential type things are harder to deal with than linear things, that this is much easier to deal with. So as you'll see, like the stuff where you're doing, estimates that have to do with exponential or natural log functions are really tedious and take a long time to do. And all of a sudden you get into something like this and it's just easier to deal with. So anyway, that's this was my another attempt at trying to get you guys to like kind of get yourself wrapping your head around what the small signal model means and why we use it, etc. And again, the other thing that I went through, I don't know, it was a couple of weeks ago, I was trying to show you guys how using feedback, etc., that this very narrow operating mode of a very small change around an input is actually a very broadly useful function, because by using these feedback methodology, etc., we can do a ton of stuff with that. So it's not like, oh, I've like gotten this simplified model because I've got, I've created this really unrealistic situation where there's a small wiggle around something and, it's only usable in a minority of cases or a very limited case. That's not true. And you can, like the majority by far of cases, you can use this. I mean, every case I've seen. I mean, it gets more complicated in real life, but anyway. So that's where I am. So now let me just check the chat, see if there's any questions. Okay, so let me pause here. Tell me your doubts, fears, understanding, whatever. Any questions about small signal models? Anything? No? Gotcha, Brandon. Thank you. Anyway, so hopefully it's good. So now let's I am going to do some remind you guys of something we did. So just do some examples to see how this works out. And then we're thankfully, and then we got one more complex, so one more concept to talk about bipolar transistors, a couple more concepts, and hopefully we're done. With the transistor, then we're going to move into the circuits. Okay. So I did an example. See, this is small things. So I did an example last lecture, and Jonathan had a one sentence question that got me thinking that I need to talk a little bit more about it. Okay, so so we had this example, I think, let me just remind you the example of, I think it's example 4.10 in the book. And it says, okay, I got this bipolar transistor and it's got a certain supply. Yeah, and then it's got a ground, Q1. There's a little wiggle of a voltage on the input. And then there's this biasing battery here. So, you know, basically this thing is here. This represents a constant voltage. So there's no signal associated with this. It's just in series with the signal to create the bias condition. So if I put now by putting, and then the signal, I forgot, signal from a microphone, it doesn't really say how much it is. But let's say I draw the voltage here. So I'm going to put VB. So if I draw VB as a function of time, so this would be voltage, it's going to look like I have a, so let's say it's something like this. And then basically it looks like an 800 millivolt offset caused by this guy, which is constant. And then this voltage source, my signal, which has to be a small number for the small signal model to work, riding on top of that 800 millivolts. So this is my actual signal riding on top of a flat 1800 millivolt signal. So that's the idea behind the biasing. So this 800 millivolt thing biases me at an I sub C that I want to get for a particular transconductance. And then that transconductance gets multiplied by my small input voltage and gives me an output here. Okay, so the question is, come up with a small signal model for the circuit. And, you know, to do that, there's, we said there's like, there were 3 steps. Okay, I think I said 2 steps in the last class, but it's really 3 steps. So 3-step procedure. 3 steps to come up with small signal model. Okay, 1. So you basically come up with bias point numbers. So basically this means calculate I sub C. Sometimes you have to calculate I sub C, sometimes you have to calculate VB, and then you have to, so calculate I sub C or VBE, depending on the type of model. In this case, VBE is given to us. So we have to calculate I sub C to come up with the bias point. That basically tells us, okay, I am biased here. Okay, wherever that is. Okay, and you also here, also very important to double check that the base collector junction is reverse biased. So it's really easy to, so in some other, like in not, well, actually, I don't know, I don't know if you see that in the homeworks in chapter 4, but definitely in chapter 5, they won't give you VBE necessarily. You'll have to come up with your own VBE to get a particular, to get this circuit to do something in particular. And so you could easily screw things up that this collector ends up being, voltage ends up being in the wrong place. And then the assumption that you are in forward active mode breaks down and you're screwed. Okay, so you have to double check to, and you are in forward active mode. Okay, so number 2, you calculate small signal parameters. So there are some additional ones, but for the time being, that's just G sub M, which is I sub C over VT. And oops. And R sub pi, which is beta over G sub M. So, once you figured this out, whoops. Once you figure this out, you should be pretty like home free. This is all you have to do is plug it in here. So once you know what the I sub C is, and you make sure that you're in the right bias condition, is just divided by V sub T, and R sub pi is just beta over GM. Okay, so thirdly, you draw the small signal model. Okay, so now that is a little trickier, because while you draw the small signal model, you have to remember the following. Okay, you have to remember that the small signal model is, the idea is that we have it doesn't exist in a vacuum, okay? You've superimposed this model on top of this model. So that's why you're calculating a bias current, and then you're sort of pasting it onto this, because what you're pretending is going on is both of these two things are kind of connected in parallel, okay? And this thing handles the bias point, and this thing just handles the small wiggle. Okay, any questions about that? This is very, very important. Okay, so both of these, it's not like I just got rid of this. I'm saying that this part handles all the constant stuff, the non-changing stuff. Okay, the bias, so the battery, and the big, where I'm based at, and I'm pasting this thing on top of this thing. So collector to collector, emitter to emitter, sorry, collector to collector, emitter to emitter, base to base. And I'm going to dump all the varying stuff, all the stuff that's changing onto this model. All the stuff that's constant stays here, all the stuff that's changing is here. Okay, why is that complicated? Okay, for a couple of reasons. So, and let's look at this. So here, so I have a constant voltage here, and I have a constant voltage here. Okay, so let me first draw the transistor. So okay, so my in this example, we did it last time, so I'll just come up with the numbers. So in example, okay. So in example, we ended up with, with I sub C ended up being 6.92 milliamps, and all we did was use that I sub C as I sub S exponential of VBE over VT. They gave us VBE, VT is a constant, and they also gave us I sub S. Did they? Yes, they did. I'm just going to say I sub S is, they did give us I sub S. 3 times 10 to the minus 16 amps, and they also give us beta. Okay, so then GM ended up being 6.92 milliamps over 26 millivolts. And that is 1 over 3.75 ohms, or 26.6 millisiemens. So it's MS. And R sub pi is beta over G sub n is equal to 100 over 1 over 3.75 ohm. 375 ohms. Okay, so I'm going to draw the circuit. So I got R sub pi here, and this is 375 ohms. And this across this, the voltage across there is V sub pi, and then when I have I got GM V sub pi here, and so that's equal to 1 over the 3.75 ohms times V sub pi, and so when I got my base collector, and then there. Okay, so that's what my device looks like in small signal. But I'm not done yet, because that's just this guy. But how about this stuff and this stuff? Okay, so this is why it gets complicated. So this is gonna, maybe I mentioned it, maybe not, didn't give it the right emphasis. So this is really important. Okay, so this is constant. Okay, and this is constant. Right, that means that we do not want to add these to our small signal model. We already use them in the large signal model. We use this to calculate I sub C, and we use this to check to make sure the base collector junction is reverse bias. So we're not going to use them again. So what happens in the small signal regime? Okay, in small signal, a voltage source, a constant voltage source becomes a short. Okay, it's just a straight connection. And like a current source, if it's a constant current source, it ends up being an open. Okay, so this is really important. So what do? Okay, well, the emitter was already connected to ground. So it is a, let's keep it in red. The emitter was already connected to ground. Okay. On my input, I have this changing input voltage. Well, that's got to end up in the small signal model. So changing voltage. But then this dude is just a short. So it's just going to look like I have, it's going to look like that. And then even more confusingly, this guy is going to be a short. There's no resistor, just a short. So it's good. It's going to be a short. So that's what the small signal model looks like. So the important thing to remember, you're just in the small signal model, you're just sticking in the wiggling things, the changing things. Okay. And so what that means, practically speaking, is if you have a constant voltage source, it just turns into a short. Okay, you see constant current sources less often, but sometimes you do, and that'll just kind of look like an open. Any questions about that? Okay, so let's see. What else? Another example. Okay. What else do I want to say about this? Okay, so let's do a sort of a sanity check. So So what I'm telling you guys, hopefully starting to sound familiar. So we're saying we've got a bias point, and if we have a small wiggle here, then we can use this simpler model, which is multiplying stuff and these constants. Okay, so now, you know, a question would be, well, what is a small signal? How small does a signal have to be for it to qualify as, you know, a small quote unquote signal? And the answer is very small. So that the key point about the small signal is, if you're looking at I sub s exponential of VBE over VT, okay, if you're looking at this equation, right, the idea about the small, so let's see, so what do we got? We got I sub c is I sub s, if we divide this up, you're going to have a V bias plus sort of a V signal over VT. So your overall signal is, so what we're saying is, if this is small enough, I'm going to kind of replace, so this kind of looks like this, I sub s exponential of V bias over VT times exponential of the signal over VT. You can kind of do that because they're exponentials. Okay, so I'm saying that if this is small enough, if this ratio is small enough, okay, I can just pretend this is like a resistor. Okay. Yeah. So what does that mean? What does this ratio mean being small enough? So the important thing is that V signal, whatever this small permutation is much smaller than VT. Okay. So when we're saying small signal, it's not that the signal needs to be small, much smaller than your bias voltage. That's not what we mean. We mean it has to be smaller than this constant V sub t. And then, you know, V sub t again at room temperature, it's around 26 millivolts. Okay. So that's what we mean. So maybe like, you know, 1 millivolt or 2 millivolts, 3 millivolts. Those are small signals compared to 26 millivolts, where you can just pretend like this exponential is like a small value. Are you guys familiar with Taylor series expansions by any chance?
I don't remember off the top of my head, but I know I've done them.
We did them at one point.
Yeah. So I'm gonna do something I shouldn't do, which is like ad lib this. So if you want to think about this mathematically, I was kind of like just waving my hands, but so, you know, avert your eyes if you don't want to hear my mathematical explanation here. So a Taylor series expansion is when, you know, you have you take something like a particular case would be like an e to the x has this Taylor series expansion of, you know, 1 plus, you know, x plus x squared over 2 plus x cubed over, and so on, dot, 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 dot. Okay, that's sort of like your Taylor series expansion. You're getting some kind of a, I guess, geometric series. God, I hope there's no mathematicians in the class, or you guys will want to shoot me. But I need some rest. Come on, John, come on. So anyway, So this is Taylor series expansion here. Okay, so what we're saying is if let's do a Taylor series expansion on this guy. Okay, so we're gonna do I sub s. I'm gonna keep V bias over VT. So I'm gonna keep that part. This is our large signal value, and I'm gonna multiply it by this Taylor series of this guy. So it'd be 1 plus V signal over VT plus, V signal over VT squared, what did I do, over 2, blah, 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 blah. Okay, so basically this is allowed. Again, they're going to do a Taylor series expansion, and this is like, it's not even, I'm not even sure this is approximate or actually equal to, but as long as this is sort of an infinite series, geometric series, it's kind of equal to, right? It's only approximate, I think, if I start cutting off stuff. So what I'm saying is if V signal over VT, oops, is like much smaller than 1, then it turns out if I square that, imagine something like, I square 0.1, I end up with 0.01. Okay, this guy start being a very small number compared to the 1 and compared to this first term. Okay, so this is what I'm doing, is I'm saying, well, okay, I Taylor series expanded the wiggly part, the changing part, and then if the term in the exponent of the small part is much smaller than 1, I can just say these terms higher than the first order term and the 1 are so small compared to these 2 terms that I can ignore them. That's the idea here. So this guy, the 1, gives me the large signal value and this wiggly thing, which, is just gonna look like a small wiggle on top of stuff. So that's kind of like my hand wavy. It's still hand wavy, God knows my mom did not give birth to a mathematician. So there you have it. It's a Taylor series expansion. And this is what we're doing. The assumption is we're making the signals much, much smaller than V sub t. That's why that's the criterion and not something to do between the signal and the bias. Okay, so anyway, now whoever was averting their eyes from my bad math can look again. Okay, so now let's use an example. Okay, so let's say if we take this case, okay, that we're playing with, and let's calculate the change in output current in 2 separate ways. Let's use the small signal model to see a small wiggle, and let's just use the large signal model and see what inaccuracy our small signal model does. Okay, so let's say say everything was the same. So in our example, let's say we have the V or V, what do we call it? V signal, V in, V1. Sorry guys, I'm using a different value. So V1 is equal to V signal, is equal to what else did it call it? Is equal to V in all these cases. So I apologize for all these different things. But let's say V1 is 1 millivolt in this case. Okay, so we want to see how much change do we get in I sub c. Okay, so let's say we use small signal model. Well, in this case, it's pretty easy. Well, 1 millivolt is a small number compared to V sub t. So if I want to see how much I sub c changed, I just multiply the V sub 1 by transconductance. I had the transconductance from the, calculated, where was it? Here, right? It's 1/3.75 ohms times 1 millivolts. And I'm trying to pull a stunt here and not use my calculator. And I'm failing very desperately. Okay, so I would still need to use a calculator, but it's an easier calculation. I guess you could kind of do it. You end up at 0.267 milliamps or 267 microamps. Okay, so this is the small signal method. Okay, now let's say I use the large signal. Again, I'm just trying to see how close I would be, like how good is the small signal model. So I use the large signal model. I have to do the following. I have to first come up with IC1 at calculated at 800 at 800. Well, I already had it at 800 millivolts. So at 800 millivolts over VT, we knew that was 6.92 milliamps. And then I need to do IC2 at I sub s exponential of 801 millivolts over V sub t. And that is 7.19 milliamps. So the delta I sub c here is 0.27 milliamps or 270 microamps. Okay. So this is the number I came up with my small signal calculation. This is the number I came up with my exponential calculation. And the idea is that, exponentials are just hard to deal with. Again, you got to remember I have a single transistor in this case. And okay, I got exponentials. I still have to there's no way I could do it in my head. This guy, this guy could do it in my head. This one, I'm unwilling to do it in my head. So I was cheating, but I guess you guys are young. Theoretically, this is a simple calculation. This is a more difficult calculation, and things get more and more out of control here with these exponentials and things as you add more devices. And as you can see, when the V1, when your input wiggle or input change is small, they are give very, very close values. And it just gets less and less realistic as V1 gets larger and larger. Basically, our assumption that we can ignore these terms in these higher order terms in the Taylor series expansion, that approximation gets worse and worse. And furthermore, we start ending up with what are called harmonics, right? We're going to end up with like higher order terms that are going to cause basically nonlinearities, which is probably a little too much to talk about in this class. Okay, any questions about that, guys? Okay, so now, just when you thought everything was simple, I'm gonna come back to Jonathan's question, which was, well, this kind of looks pretty easy, right? You got your, is this all you have to do? Well, these 3 steps is all you have to do. But so far, so good. This looks kind of easy, right? Like, I got a VBE, I'm good to go. Okay, but not so fast because, this is kind of an easy one to think about because I'm nailing down my VB pretty definitively. Okay, so let's say I do something else. So this was, I was looking around for an example, and this is where things get more complicated. This is why you need a lot of practice. So I was looking at it. I was looking at trying to show you guys, I think, a good representative problem, 4.22b in the homework. Okay, so this is what the circuit looks like. Whoops. Okay, so this is something that like really gets a lot of people, like a circuit like this, because notice something. Now, my base is connected to +2 volts. Okay, so I got my, remember I need, first thing is I got to figure out the bias point, or that's part of my set of activities. Okay, so how do I come up with the bias point here? So I need to know like what is I sub C. I don't even know VBE because why? Because my emitter is no longer connected to ground. It's sitting somewhere here connected to this resistor. And at this point in time, I don't know the voltage at VE. I don't know what that is. I know the voltage at, so I need to find VBE. So I have VB, that's 2 volts, but what is VE? I don't know what that is. So be really careful with that. Don't just say, oh, I know my VB, so my VBE is just the same thing. That's, you know, you have to make sure that, you know, that your base and emitter, that's the bottom line, is you just need to know what this voltage is. Not the difference between this and ground, but this and this. So, and then so you can see it here. Okay, so I'll work this out for you guys because it's not really that simple. We still do, we still go through the same 3 steps, right? But this is what, it's the same 3 steps. Figure out the bias point, calculate G sub m and R sub pi, the small signal models, and then you draw the small signal model. Okay, that's what the problem asks for. But the reason you need practice is because there's all these circuit configurations that are a lot less friendly to look at than something as simple as this. Okay, like basically this is like, what do I do with this? Okay, so let me just do that. So what do we do? Okay, so okay, so I can do a KVL here at this point. Okay, so I have this voltage minus VBE. So this is VBE, but I don't know what it is, but it's just VBE. Okay, gives me this voltage here. Okay, so if I was gonna write, so let's see, so VCC, which is VCC is 2 volts. VCC minus VBE minus the resistance, what do we want to call this? I want to call this R. V at R is equal to 0. Okay, so I'm doing a KVL here. This voltage minus, so that's this node minus this voltage VBE minus this guy is 0. So I'm starting at 0. KVL in here, going across this, and then you go back at 0 again. Remember, these two are connected together when we're grounded. Okay, so basically, VCC is VBE plus VR, and VR is I sub E times R. That's the voltage across this guy. Okay, so now right off the bat, I'm going to make an assumption that I am in forward active mode, and I'm going to come back and check this assumption. Okay, so I'm going to come back and check this assumption. So if I'm in forward active mode, okay, if in forward active, I sub E is equal to I sub C plus I sub B, and IE is equal to I sub C, and then I sub B is I sub C over beta. Okay, so I must have been given beta on this thing. But beta is, let's say it's 100, right? So what I can say is this term here, this term here is the same as this term, but like 100 times smaller. So I can already say that I sub E is approximately equals to I sub C. Okay, so I can rewrite this as V sub R approximately as I sub C times R. So I'm gonna plug in VCC is VBE plus, what am I doing here? Sorry, guys. Let me make sure there's only so much ad hoc stuff I can do. I'm gonna look at things here. Plus I sub C times 1 kilo. And I sub C is, start a new page here. All right, is everybody with me? You guys doing okay? Let's see if
On the right hand side again, what did you say happened to I sub C over beta?
so what I'm saying is that, what am I saying here is I sub C over beta is much smaller than I sub C. Because
Okay, so that's just like the Taylor series thing that you showed earlier.
well, it's only like that in the sense that I'm using this like much smaller than, but this is just straight division, right? If I say if beta is 100, then you take any number divided by 100 is much smaller than itself. That's all I'm saying.
Okay,
Because this is the number, this is the same number divided by 100. Does that make sense, Brandon?
yes, yeah.
It's all about making assumptions and simplifications. Let's see. Okay, so where was it? Okay, so then I'm gonna keep writing here. VCC is VBE. And I'm gonna just, my equation, again, I've already assumed that I'm in forward active mode. So I sub C is I sub S exponential of VBE over VT. So this is I sub S exponential of VBE over VT. And which times a kilo. This VCC is 2 volts. So 2 volts is VBE plus, the problem gave us I sub S at, what was it, 8 times 10 to the minus 16 amps. Okay, so now I'm in an unfortunate situation, okay? So now we're in an unfortunate situation that we have, it's only unfortunate from a standpoint of your patience and time, because, you know, I have this equation. I have 2 volts on one side and I have VBE here in sort of a linear thing, and VBE in an exponential term here. So there's no closed form solution, unfortunately. So I'm gonna have a couple of choices, but basically you got to use a numerical method to come up with what VBE is equal to, and that ends up like being a series of guesses, and you plug that guess back in and you iterate and modify your guess and all that stuff. And again, the only reason that we're even able to do this is because, again, assuming that I'm in the forward active mode, which means that the base emitter voltage is forward active, I have a limited range of reasonable VBEs. So reasonable VBEs are in the range of, I don't know, like 700 to 800 millivolts, maybe 650 to 850, something like that. Okay, so I'm gonna, like, 1 volt is not a reasonable number for a forward active base emitter voltage. Just not, you know, that's, I'm just gonna make that as a claim. 200 millivolts isn't. So we can kind of start in this range. So I'm gonna assume the right good value for VB is 750 millivolts. And I'm gonna plug in. So I would get 2 volts. So I'm gonna plug it into here. And yet 2 volts is 750 millivolts plus 8 times 10 to the minus 13 volts exponential of 750 millivolts over 26 millivolts. So now is this equal? No, because this will be 2 volts and this is 3.44 volts. Okay, so that tells me, well, you know, I should pick a smaller number for VB. So I'm gonna try smaller VB. Okay, so here's another sort of word of advice or cautionary tale, or whatever you want to say it is. Go in small increments, because you have this exponential term of VBE, and you have VBE, right? But notice just the VBE itself is 750 millivolts or whatever guess I come up with it. So the other 1.2 volts or whatever this 3.44, so this 3.44 was 750 millivolts, and you know, whatever 2.5 volts that came from this equation. So a big part of my guesses are in this exponential term, and that, because I'm in an exponential, a little goes a lot. So if my next guess was, oh, I'm going to make this instead of 750, like I'm going to make it 650, that's probably going to give me a really small number here, like too small. So I'm just going to say, oh, like I'm going to go to 730 instead of 750. And hopefully you guys were able to follow that. So a lot of stuff is coming from this exponential term. And again, we don't want to vary your guesses too much because it's in that exponential. So try smaller VBE and try VBE of 730 millivolts. And then we get, of course, I'm faking it because I already knew the answer and that this would be close. Maybe it would take you guys a couple more guesses to come up with it, but this would be 730 millivolts over 26. So, and then this on this side would be 2 volts, and on this side it would be 1.98 volts. And okay, that's close enough. So VBE is approximately 730 millivolts. So you guys see what I'm doing here? Because I ended up with the situation where I don't know what this V emitter is, and this emitter voltage is a function of the current through this resistor, but the current through this resistor is a function of the base emitter voltage. I have to like do this iteration thing and try to figure out what's, there's, one number that fits that, but we don't know what it is. So we have to sort of iterate to see what makes sense. Okay. So we end up with 730 millivolts. So now using that, I can do I sub C is 8 times 10 to the minus 16. This is I sub S times exponential of 730 millivolts over 26 millivolts is 1.2 milliamps. Okay, so that's my I sub C. Cool, so that was step one. It was painful, but that was step one, okay? So I figured out my bias point. So now things get a little bit easier. I have G sub M is just equal to I sub C over V sub T, so it's 1.2 milliamps is step two. Over V sub T, so that is 46 millisiemens. And R sub pi is beta over G sub M, and that is 100 over 46 millisiemens is 2,167 ohms. Okay, and then drawing the circuit. So I got my R sub pi, so this is step 3. This is R sub pi, which is 2,167. And then I got my G sub M. So remember where V sub pi is. It's across this R sub pi. Okay, so that's equal to 46 millisiemens times V sub pi. Okay, so that's my device. Now I got to figure out what to do with all these nodes. Okay, well, the base is connected to the collector. Okay, so just gonna connect those up. I'm gonna draw that in red. So I'm gonna connect the base to the collector. My emitter is connected to a resistor that's connected to a ground. Okay. So resistor connected to ground. Okay, now the last term is this voltage source. And this is like the thing that like, I don't know, I always like shudder to do this, but we promised we'd do this. We're gonna short the batteries, the voltage sources. So it's gonna be a short. So this guy's gonna short the ground. So this is going to short the ground. And that's my third step, my small signal model. Just in time. So that was, Jonathan, that was for you. Like basically the steps are always the same 3 steps, but the reason you need practice is because there are all these like funky coming up, especially coming up with this first bias point is not always like straightforward. You need practice to, because there's lots of different circuit configurations that you could end up in. And you need practice to figure out what this means and where that puts you. The step 2 is almost always easy because it's just plugging in numbers. Step 3 is also a lot easier than step 1, but don't take any shortcuts, right? Just apply the rules, make sure the nodes, if you see something in a node, no matter how funky it looks, just follow what the schematic tells you about what to short together and what to short across. Okay. Any questions, guys, before I let you go?
Hi, Professor. I had a really quick question.
Yeah,
So, when will our next midterm be?
good question. You know, I'm not good at keeping track. When should it be? Is it coming up? Was it supposed to be this week?
Yeah, I think it was supposed to be this week.
Ah, always messing up. Why don't we make it, what week are we in? This
We're
is,
in week 10.
and we have, help me here, guys, you have 15 weeks in the semester or 16? How many instructions? How many weeks of instruction? 16 or 15 or what is it?
Yeah, I think it's 15 plus finals week.
Gotcha. Okay. Well, this is kind of pushing it a little bit. So I'll put this on, but I think we should have the midterm not next week, but the Tuesday after. How's that? So we'll that'll give you guys time to do
So the 9th,
homework 3, 9th. Yeah, it sounds right.
Will it be like our last midterm with like a 24-hour period?
Yeah, it'll be the same.
And will our final be like that as well, or is it going to be timed at a certain?
No, it'll be also 24 hours.
Okay, thank you so much.
Sure. Any other questions, guys? And then the midterm is just gonna cover chapter 4, basically kind of like stuff we're covering in homework.
so this,
What's that?
it'll cover this.
Yeah, I'll cover this, basically stuff in homework 3. I mean, well,
Can you scroll back up for a second?
sure.
Keep going. Yeah, at the very beginning. So I sub E on the right hand side, you have it equals I sub C plus I sub B.
Mhm. Yeah,
So is that just
oh, why do I have that? It comes, is that what you're asking, Jonathan? Sorry.
yeah,
Yeah, so it just comes from, you remember, you know, it's been like a few lectures, but from the operation. So we basically have, looking at the bipolar transistor, we had a current I sub C, we had a current I sub B, and we had a current I sub E. Because we have 3 terminals, so there's currents for each terminal, just like we put voltages on each terminal. And if we're in forward active,
and then just KCL thing.
yeah, you're just summing up I sub. So let me just write it for everybody. That is I sub C. The I sub B is just I sub C over beta, and I sub E is I sub C plus I sub B. So whenever you're in forward active, except in very, very few cases, you can pretty much assume I sub B is the same as I sub C. I mean, they're gonna be, by definition, they're gonna be like a percent or whatever different, which for most of our cases, doesn't matter. Any other questions, guys? Okey dokes, well, have a good weekend.
Enjoy your weekend. Thank you.
Bye.
Professor.